In this video, we are going to talk about understanding load paths in light frame wood construction. My name is Chad Johnson. I'm with Truss Components of Washington. I've been in the truss industry for over 30 years, and I'm excited to talk to you about this topic. All right, let's answer the basic question. What is a load path? Simple answer is it's where does the weight go? In any structure, there are a lot of different materials and environmental forces that need to be taken into account. So when we say, where does the weight go? We always need to get everything back to the ground. So we're going to have the weight of a snow load, for instance. We'll have the weight of the materials that make up the roof, the weight of the materials that make up the trusses, the walls, the floors, everything in between. And we want to get all of that weight down to the foundation and back into the ground. Additionally, we have other sort of loads, such as live loads of inhabitants in the building. We have the forces of wind on the structure. We also have seismic or earthquake forces where the ground itself wants to move underneath the structure. And the structure needs to be designed so that all of these forces move through the structure and down into the foundation and back into the earth. Let's start with gravity loads. Gravity loads always need to make it down into the foundation. And so how would we do that? Well, if we start out with something simple like a roof truss, that roof truss is going to take the loads that are imposed on it, the snow, the weight of materials, and they are going to transfer those loads out to the bearing points. So underneath those trusses, we need adequate support to transfer that load back down into the foundation. So there are a bunch of different ways to do that. One is within a wall. Up here in the Northwest, we typically build with a double top plate, which allows trusses to land either over a stud or in between a stud in a typical 25-pound snow load situation. But we have girder trusses that often carry large portions of the building. And under those girder trusses, we need to make sure that we have studs that are equivalent to, studs or posts that are equivalent to the number of plies of that truss. And so all of these gravity loads that are being imposed on the truss are going to transfer from the truss through the top plate and down into the studs. When we run into a situation where maybe we have an opening in the building because we have a window or a door, then we're going to have a header over that opening, and that header is going to transfer the loads out to the studs on the sides of the opening, and that load path continues down, and we're eventually looking to get to the foundation. So underneath that wall, we'll have a concrete foundation, and that concrete foundation will take those loads and transfer them into the earth below. If we leave out these supporting members, then what happens is, for instance, if we have a door or window opening that does not have a header over it, then that load does not get transferred to the studs on either side of the opening, which would cause the members above that window to bow and potentially fail, causing at a minimum aesthetic concerns, but potentially a structural failure of that portion of the building. In addition to the gravity loads, we also have what we call lateral loads. So those lateral loads are wind or seismic forces that place a force against the side of a building. And so in order to prevent the building from toppling over, we need to be able to resist those forces. And so those lateral forces are typically resisted by sheathing or some other method of bracing the structure that transfers those loads back into the foundation. So, for instance, a sheet of plywood that is nailed to a set of studs will take those forces, and because you can't twist or distort that piece of plywood, those forces get transferred back into the foundation without allowing the building to be distorted. The same is essentially the way that the loads are transferred for a seismic force. The difference being that in a seismic situation, it's the ground that's trying to move and the building needs to stay rigid while the earth tries to move under it. It's essentially like the lateral wind forces, just flowing in the opposite direction. One typical area of confusion regarding load paths and how to transfer them is Gable and trusses. With each truss package that we provide, we send out recommendations for bracing that gable end, and it's likely that you will also have instructions on the set of blueprints that you're working with. Those instructions have either been provided by the home designer or by the engineer on the project. But when we talk about trusses, they are designed using materials like 2x4s. The 2x4s have a narrow plane and a wide plane, and that wide plane is not as resistant to forces as the narrow plane is. So when we take a look at a gable truss, for instance, that gable truss, it may be a big triangle that is 30 feet long or even more and has vertical studs in it. That's one direction to look at it, but when we turn that gable truss and look at a cross section of it, it's only 1.5 inches thick. And so that material isn't really designed to resist the lateral forces of the wind that are going to be applied to it on a regular basis. And so in order to resist the temptation of that member to buckle under those forces, we need to put bracing on that gable. So this is not a specific instruction, it's just a reference to recommendations, but oftentimes there will be members added to the face of that gable, and it will be braced either up to the roof or it will be braced down to the ceiling, and that takes the load from the wind and it gives it a path to get back down into the structure or up into the roof structure, where that load will follow through the roof sheathing and eventually end up being transferred back into the walls and then down into the foundation where every load needs to go. A simple way to follow a load path is to ask yourself the question, what am I supporting and where does it need to go? I'm going to take sort of a complicated example here, but it's one that we come up against regularly in the truss manufacturing world, and that is a dormer in between some attic trusses. So it's not uncommon for us to build a garage, let's say, and over that garage, we're going to have some habitable space. The cross section on the truss on that garage might look like this here. It is what we would refer to as a room in attic. And so this space here is usable for storage or living space, however you like. And oftentimes people like to put what we call a dormer on that, which allows to get a little bit of light in, a window. And from the top, it might look like this. From the side, it would look something more like this. And so now we have introduced a bunch of loads in the center that need to be transferred to the outside. So to look at a slightly simplified version of that building, what we have is a set of standard room and attic trusses at a regular spacing, probably 24 inches on center. And then on each side of that dormer, we have a girder truss. And so that girder truss is going to support all of the loads in the area between it. So when we look at, okay, what are we carrying? Where does the load need to go? So these trusses are carrying this dormer area inside. So the end view of that. That could be our girder trusses there. So these are carrying the weight of the center. So that's going to go onto those girder trusses. We need to carry that load from the girder trusses into the wall. And like we talked about earlier with girder trusses, we want to match them with a post or studs. And so that load's going to go through the top plate. It's going to go into a set of studs that matches the girder. And then those studs are going to transfer that down to the foundation, which in turn will transfer it down to the earth. So anytime we have a load up above, we need to carry it all the way down to the earth. If we have a load from a wind, we need to carry that down to the earth also. So far, we've primarily talked about gravity and lateral loads. One load that we didn't talk about is uplift. A truss is kind of like an airfoil or an airplane wing. And when wind blows over a truss, it creates uplift. And so that actually creates a force that wants to raise the truss off of the walls. And so that force needs to be resisted as well. Just like every other force, it needs to be carried all the way down to the foundation. And so in our foundation, we may have tie downs or rods or bolts that are attaching to the studs. That tie down will keep the load in the foundation, and that load will be pulling up on those studs, and we need to resist that at the truss with what we typically refer to as a hurricane clip. But there again, every force in the building needs to be transferred back down to the ground. So many of the forces are going to be transferred through structures to resist gravity, and other forces are going to be transferred through structures to resist uplift and the lateral loads. In conclusion, every load needs to be transferred to the ground, anchored to the ground, traveling to the ground, whether it is a load from snow, a load from the material weights, a load from people, a load from wind, a load from the earthquake. We always want to get that load properly supported securely to the ground. If you want to learn a little bit more about the anatomy of a truss and how we might design it in order to resist those loads, you can look at this video here. Or if you'd like to know just more about what types of trusses are available, you could take a look at this video here. Thanks for watching.